Okay, let's get started. What we want to talk about today are the photonic materials, or the optical properties of materials. There are a number of reasons for being interested in the optical properties of materials. The first is optical properties were a good part of the very earliest development of material science, and their main concern was things like the people were interested in objects that were beautiful, and they're beautiful because they appeal to your eye with their beauty. Pottery, glazes on pottery were part of the initial Stone Age, and in fact the development of glazes was a major part of the development of the chemistry of materials. Jewelry, you can go back to almost every new material that was introduced, from stoneware to steel to aluminum to gold. And the very first application of virtually all of those materials was in jewelry. The first artifacts, the oldest artifacts, are either jewelry or religious objects. So the appeal to the eye or beauty was a very real motivation for the development of material science. The second thing we do with optical properties are information. The ancient way of using optical properties for information was the development of window glass, things that would protect you from the elements but nonetheless let you see outside. This is very old in human history, and of course transparent window glasses until fairly recent was a very valuable and expensive commodity. In the Middle Ages, the kings of Europe, moving from castle to castle, would take their windows with them and mount them in their new place of residence whenever they changed residences for a while. Now optics have come to dominate large segments of information. We used to transmit information by smoke signals and such things. We went from there to transmitting it through copper wires, and now a very large fraction of all the information that's transmitted in the world is transmitted through optical fibers, through optical signals that travel through things like light pipes. Light, the production of light to improve visibility, the electric light, LEDs and lasers, photodetectors and photoconductors that are so important in engineering today. And finally, we use the optical properties of materials for power. Classic example of photovoltaics, like solar cells. We also transmit power by a laser power transmission or microwave transition or other uses of the optical properties of materials to transport power from one place to another. So there's an awful lot of engineering that gets tied up in the optical properties of materials. A couple of things to keep in mind. The first is that when we say optical, we really mean the whole electromagnetic spectrum. Photons, visible light, and such things are electromagnetic waves. There's an entire spectrum of electromagnetic waves, and there's only a tiny sliver of that constitutes visible light. In fact, the response of materials to electromagnetic waves is in general. It has nothing to do with whether it's visible light, ultraviolet, or infrared, or lower frequencies. So we're talking about the entire spectrum of the electromagnetic radiation. Electromagnetic radiation, as you know, can be regarded or can be treated as either waves, light is the propagation of a wave, or particles, light is the propagation of a stream of photons. And the original development of quantum mechanics, or the recognition of the need for quantum mechanics, came about because scientists were puzzled about the dual properties of light. Sometimes it acted like a wave, sometimes it acted like a particle. When it comes to engineering, we make specific use of the wave properties of light for some engineering application and the particle properties of light for others. The wave propagation of light, refraction, reflection, and interface, we use in windows, light pipes, solariums, things of that sort. The absorption and scattering of light, which we use in optical fibers. The diffraction of light, X-ray, and well, electron isn't quite electromagnetic waves, but crystallography, the diffraction of electromagnetic waves. Light also is particles. Using light as a particle, we can understand a great deal about how light is transmitted and absorbed. We use the particle properties of light in photodetectors, photoconductors, for switches and photocopiers. We use the particle properties of light for photoemitters in LEDs and lasers. So I'll try to sketch out the properties as they pertain to all of these engineering applications. First of all, remember light is an electromagnetic wave. An electromagnetic wave is a simultaneous electric wave and magnetic wave. The electric wave, however, is much stronger. The electric field carried by an electromagnetic wave is much stronger than the magnetic field. So we can often ignore the magnetic component of the electromagnetic wave and can consider it simple as an oscillatory electric field that goes like exponent I kx minus omega t. K is the wave number of the light, 2 pi over the wavelength lambda. Omega is the angular frequency of the light, 2 pi over nu. The speed of the particle of the light is omega over k nu lambda, which is c, the speed of light in free space. In materials, this has a slightly different value, as we'll see in a minute. As a particle, the light is a stream of photons. The photons have an energy which is proportional to the frequency of the light, h nu or h bar omega. Here's the whole frequency spectrum. Electromagnetic waves have the same character as we take the frequency from something like 10 to the 4th up to 10 to the 22nd, or as we take the energy in electron volts from 10 to the minus 10, this is the photon energy, up to 10 to the 8th, or the wavelength from a kilometer to an angstrom and even less. There's a huge continuum of electromagnetic waves. Mathematically, they're all the same. In the fundamentals of their interaction, they're all the same. However, the specific ways in which they interact with materials are rather sensitive to what their energy or wavelength or frequency are. The visible spectrum is a very tiny sliver here near 1 micron. We start from red at about 7/10 of a micron down to violet at about a little less than half a micron. And this tiny little sliver of the visible spectrum is what we can see. When we talk about the optical properties of materials, it's important to recognize we're not just interested in that tiny little sliver. Of course, we're interested in it because that's what we can see. But the engineering applications of the optical properties of materials go through the entire spectrum. Light is a wave. The first thing to recognize that light is a wave is that first of all, it propagates through space at the speed of light, at velocity c. But we become interested in it when it enters a material. So let's imagine an incident beam of light, wave, coming in from free space and contacting some material. When it contacts a material, 3 things happen. The beam of light is refracted, that is, when it enters the material as a transmitted beam, assume this is a transparent material, its behavior inside the material, specifically its speed, will be different from its behavior in free space. The second thing is that it is reflected. When we bring light from free space and it's incident on an interface, some of it will be reflected back. And finally, it's attenuated. When it comes into the material, it not only behaves differently than in free space, but the intensity of the light beam will gradually decrease as it traverses into the material until finally it will disappear, unless this material is very, very transparent. Refraction. What's happening in refraction? Why is it that a wave, when it enters a material, behaves differently inside the material than outside? Well, the reason is really very simple, and it kind of has to do with the behavior of dielectrics that we talked about last time. Because after all, the dielectric is, the behavior of a dielectric is its response to electric fields. And the light wave is an oscillating electric field. Well, now that oscillating electric field is normally going to interact with the material. As the oscillating electric field interacts with charges in the material, those charges, the movement of those charges, effectively put a drag on this light wave coming into the material. And as a consequence, the wave inside the material is dragged, friction slows its propagation. Imagine this as a runner running along and suddenly he hits a field of heavy sand. He slows down because of the difficulty of running through the sand. That friction slows him down. That behavior, the refraction of light within a material, is governed by a property known as the index of refraction, which has the symbol N. It's actually related, as you would think, to the dielectric constant. The reason we have refraction or a difference in behavior is that the electric field is responded to by the distribution of charges in the material. As a consequence, the dielectric constant is related to that charge distribution and its response to an electric field. We would think that the index of refraction and the dielectric constant would be related too. And in fact, you can show mathematically, I'll just assert it, that the index of refraction is the square root of the dielectric constant. Well, when we talked about the dielectric constant or the behavior of dielectrics, we recognized that the dielectric constant was the sum of a number of different things that could happen with dipoles in the material, and that those different things would have different time constants. It takes a while to flip a great big polar molecule. It takes much less time to excite an optical vibration, which moves ions, and even less time to excite the internal dipoles within atoms. As a consequence, as the frequency increases or changes, the dielectric constant of the material will change, and as a consequence, so will the index of refraction. If we come back to the equation that governs the electromagnetic wave, the electric field exponent ikx minus omega t, in free space, if the wave number is k0, inside the material it will be n k0, where n is the index of refraction. And that tells us that the wavelength in the material will be decreased to lambda 0 divided by n. The frequency, omega over k, turns out to be the sound speed in free space divided by the velocity of the wave in the material, omega over k, is the speed of light in free space divided by the index of refraction. So if the index of refraction is greater than 1, as it normally is, the speed of light inside the material is less than it is in free space. And the constant of proportionality is the index of refraction. I should mention, it's covered in the notes, I'm not going to discuss it in greater detail here, that the index of refraction, in simplest terms, is just a number. In fact, if you look into the physics of electromagnetic wave propagation, it can be much more complicated than that. In general, the index of refraction is in fact a complex number. It has both a real and imaginary component, and the imaginary component is related, for example, to the attenuation of the wave. For our purposes, to keep life simple, let's focus on the real part of the index of refraction and assume it's always greater than 1. There are also situations, and these are described in the notes, in which the index of refraction can be less than 1, in which the speed of light in material can be actually greater than it is in free space. But I'll leave those to the notes, and we'll focus on the more common, usual situation where the index of refraction is a number, and that number is greater than or equal to 1. What are the consequences of refraction? Well, one of the principal consequences of refraction is the bending of a beam of light when it hits an interface at an angle. And that's given by Snell's law. If we imagine two parallel beams of light impinging on an interface, coming from an interface with index of refraction n, going into a region with index of refraction n1, where we assume, because of the geometry here, that n2 is greater than n1, what will happen? Because the speed of light is different, there is an effective bending of the beam of light. And that bending of the beam of light is governed by Snell's law, which you've probably seen derived in physics. It's derived in the notes. I won't go through the derivation here, but it says that if we take phi1 as the angle with respect to the normal of the beam in the material with index n1, and phi2 is the angle in the material with index n2, n1 sine phi1 is n2 sine phi2. What this tells us is that the beam of light is bent toward the region with the lower index of refraction, the region where the light is moving more quickly. Now that has many consequences. For example, it's well, not only is it bent, but since the index of refraction depends on the frequency, depending on the frequency, it will be bent more for some frequencies than others. And this is the basis of creating a prism, for example, that breaks light into its components and produces a rainbow. The amount by which light is bent inside a piece of glass depends on what its frequency is. But from the engineering point of view, perhaps the most important consequence, and the one I'll focus on, of the bending of light by the index of refraction has to do with the critical angle. If we allow this angle phi2 to increase, notice that the light is bent more in the region that has the lower index of refraction. So I can finally reach an angle, the critical angle phi c, which is just the inverse sine of n1 over n2, at which the beam inside the material with the lower index of refraction will actually become parallel to the surface, and the light will not be able to escape the region n2 at all. This is the critical angle, and the critical angle is the angle of incidence at which light just can't get out of the region of the higher index of refraction. The classic example that you probably have seen this effect since you were a very small child is in a swimming pool. You stand outside the swimming pool, you're looking for a region of low index of refraction into a region of high index of refraction in the water. There's no critical angle. You have absolutely no trouble seeing everything under the water in the swimming pool. But you probably had the experience when you were young of getting under the water of the swimming pool and then trying to look up. And what you probably observed was that you might be able to see the sun directly overhead or something almost directly above you. But if you looked at any angle at all, almost, it would look like the surface of the water would just look like a mirror. It would look like you just couldn't see those things. Well, that's the consequence of being in the region of higher index of refraction and trying to look out at angles that exceed the critical angle, which turns out to be a very small angle from water and air. So you've seen that. Well, we use that in engineering in many ways, but the most important way it is used in engineering is in the science of optical fibers. Suppose we have here a glass fiber with a relatively high index of refraction, and we put that glass fiber in air. And suppose we start sending a beam of light down the axis of that fiber at a rather small angle. Well, if the critical angle here is relatively small, then almost all of the beams that emanate from a point of light at the left-hand edge here will exceed the critical angle and will therefore be trapped inside the fiber. So the light we put in the fiber will not escape into free space, except for a tiny bit here at the origin. And it will come down the fiber, and if the fiber bends or turns, the light will bend with it, and it will come out the far end. Maybe the first place you saw that effect, gosh, they were popular some years ago, I'm not sure they still are all these little decorative lamps that have the little tubes coming out, and you light them up, and all the lights are points of light at the end of the little tubes. That's all you see. Well, obviously, you can put this to rather more important uses than that. You can use the optical fiber as a way of, for example, snaking a fiber somewhere down into your body, shining light, and visualizing what's at the end of this optical fiber. A surgeon can use it to observe the placement of things like stents and other things within the body through these optical fibers. These days, perhaps its dominant use, however, is in optical communication, where we use a pulse of light as to carry information, and we use a fiber to transmit that pulse of light with as little distortion as possible, essentially at the speed of light and with very low energy consumption over a reasonably long range. This is a far more efficient way to transmit information and a faster way than, for example, a copper wire in many circumstances, and it's so used. Yes? There are really two reasons. One is that the speed of light is ordinarily greater than the speed of current by a significant amount. And the other is that the detail that you can put into a signal optically is, in most cases, you can put more structure into an optical signal than you can an electrical signal. And that also, electrical signals also tend to disperse because of the interaction between electrons and the materials more problematically than a properly constructed optical signal in a properly constructed fiber. And I'll talk to you about that in just a minute. Anyway, this is how light pipes work. Reflection at an interface. If you send a beam of light at any interface where the index of refraction changes, there will be a reflection. Now, that's discussed in the notes, and the reflection can be a rather complicated function of the angle of incidence and reflection. For the simple case in which the light is normally incident on the surface, then we have a relatively simple phenomenon. The reflected intensity is proportional to the square of the difference in refractive index between the two media. The transmitted intensity is what's left over after this intensity is reflected. The really important thing to keep in mind, if you want to amaze your friends with your great knowledge, is that the reflection of light depends on the difference in the index of refraction. It does not depend on whether the material that you are striking is transparent or not. One of the dumbest things I ever saw in a TV show many years ago. There was a show on called Mannix. It was a private detective. He worked in Hawaii. These were black and white days. And Mannix had a problem. Someone had stolen some diamonds. Mannix was convinced he knew who had stolen them and where they were. But they searched this guy's house, and they searched this guy's house, and searched it, and they couldn't find the diamonds. So finally he had a clever idea. He went to the guy's refrigerator, pulled out his ice cube tray, melted the ice cube tray, and lo and behold, the diamonds appeared. They had been hiding in the ice. Now, you can, well, I'm not suggesting you do it with a diamond, but if you take a piece of glass, freeze it inside an ice cube, look at the ice cube. What do you see? You see a piece of glass frozen inside the ice cube because it reflects from the surface. So I said, this is sufficiently dumb that nobody would ever be this stupid again. There's a movie out there, which you may have seen because it was a San Francisco movie called The Presidio. Starred Sean Connery and, oh God, who's the guy? I'm drawing a blank. Did Top Gun. I'm sorry? Tom Cruise, yeah. So big stars. The feminine lead was also big named, I forgot exactly who. Called The Presidio. Shot here in San Francisco. In The Presidio, someone was smuggling diamonds in from the Far East. And how they were doing it, how they got away with it? They were putting the diamonds in big barrels of water. Therefore, no one could see them. Except that, try it again. Put a piece of glass into a tub of water. What do you see when you look at it? You see a piece of glass in a tub of water. Now, what amazes me about that movie was that, they shot scenes in which people would dump out the water and here would appear that the actors must have known that they could see the diamonds in the water, but they did it anyway. And, don't make that mistake. Whether you can see something has to do with whether it is reflective. If you want to make something that cannot be seen, you can do it. What you have to do is to match the index of refraction of what you're talking about to the index of refraction of the thing it's embedded in. If you can make a diamond which had the same index of refraction as water, good luck. Then you could hide it in water. Even then, you really couldn't, because this reflectivity changes quite dramatically as the angle of incidence changes. So even if you made something that was invisible at normal incidence, it wouldn't be all that obvious at glancing incident, but it would be visible. So you just can't do this. This is the way refraction works. Reflection depends on delta N, not on transparency. Of course, we use reflection all over. We use mirrors. We reflect light from one place to another. We have, for example, in a laser, you use reflective surfaces to confine the laser beam and make it do certain things. So reflectance is a rather important engineering property. Attenuation. In a material that, in any real material, the transmitted beam of light is gradually attenuated. It gradually loses its intensity as it's transmitted into the material. The simple equation that governs that, and it works pretty well, is that the attenuation is exponential, and the attenuation coefficient is eta. So the intensity of the light beam is just the original intensity, exponent of minus eta x, and it drops off exponentially as you go into the material. Now, that is true for all materials. You may think of, for example, a metal or some opaque black thing, well, gosh, there's no transmitted beam in there. That's not true. In such an absorptive media, eta will be high, and the distance of light penetration will be rather small. But there's always some penetration, and the light does get into the material. And you can kind of see that. As you take materials and make them thinner and thinner and thinner, you'll finally get to the point where they're transparent, no matter what they are. Classic example, it's a little more complicated than this, but is an example, is the chrome coating on an automobile. You have a chrome bumper, looks nice and shiny, looks like fresh metal. In fact, that fresh metal is coated with an oxide layer. And if you take a big hunk of Cr2O3, then it won't be very transparent. But on the surface of a chrome bumper, it's quite transparent. Not because it's inherently transparent, but because it's inherently very thin. And so you see that. There are two reasons for this attenuation. One is absorption, and the other is radio scattering. Absorption is kind of better viewed in terms of the photons rather than the waves, but you can think of it in terms of waves. Suppose I have a metallic conductor, for example. When I put an electromagnetic wave into a metallic conductor, unless the frequency is very high,